In this session, we'll look at the shortcuts and the tricks that we can use while answering MCQ questions, especially in further mathematics. This is a paper of GCE 2019. The first question says the integrating factor for the differential equation dy dx minus 1 over x minus 1y equals e to the x. With the case of solving differential equations using first order differential equations using an integrating factor, the first step is to ensure that dy dx has a coefficient of 1, which is already the case, and then the integrating factor would simply be e to the integral of the coefficient of y, which is negative 1 all over x minus 1, and that integral is negative ln of x minus 1, and it gives e to the ln of x minus 1 to the power negative 1. E to the ln of something gives that thing, and so the integrating factor will be 1 all over x minus 1, which is c. In number 2, we are given a complex number in exponential form, which can still be written as e to the negative 2 theta I. The coefficient of theta there, the coefficient of I there gives the argument of the complex number. So the polar form should be d. And usually when the exponential form has a negative power, the polar form would have the imaginary part being negative. That is why the answer is D. If it were positive, the imaginary part would also be positive. For number 6, they want the mean value of tan x. Usually mean value is given by integral from a to b of y dx. So integral from 0 to pi on 3. Supposed to be 1 all over b minus a, into that. So 1 all over pi on 3 minus 0 of tan x dx. And this integral, this should be 3 over pi ln of sec x. And so we're taking from 0 to pi on 3. This will be 3 over pi. Sec pi on 3 is the same as the inverse of 1 over cos pi on 3. And cos pi on 3 is half. So ln of the inverse of half will be ln of 2. Sec 0 is 0 because cos 0 is 1. And so ln 1 is 0. Though this is the answer. For number 7, we're required to find the polar equation of the curve x squared plus y squared equals to 2x. The answer is E. Directly you can see that this will be r squared equals 2r cos theta. X squared plus y squared is always r squared in the polar system, and x is r cos theta in that system. So the r's would cancel the square there, and r would be equal to 2 cos theta. In number 3, we have B as the answer. You can notice that to get this as a partial fraction, the denominator, the factor x squared minus 1 is still factorizable. So it will give x plus 1 into x plus 1 into x minus 1. So there's a repeated factor, which is x plus 1 all squared. So the partial fraction should be x plus 1. The partial fraction should be x plus 1 into x plus 1 all squared into x minus 1. So the answer is this, And then In number 8, we're asked the distance between the planes 2x minus y minus 2z equals 5 and 2x minus y minus 2z equals 7. You can notice that the two planes are parallel, and once two planes are parallel, the distance between them is d1 minus d2, the absolute value of that, all over the magnitude of their normal vector. And so this should be 5 minus 7. The absolute value gives 2 all over the magnitude of the unit vector, the magnitude of the normal vector, which is 2 squared 4 plus negative 1 squared 1 plus negative 2 squared 4. 2 all over the square root of 9, which is 3. So the answer is B. In number 4, which one of the sequences below is divergent? One quick way of getting the divergence of a sequence is to look at the uniqueness of the limit of the general term. If the limit of the general term is unique and finite, and then it means the sequence will converge, otherwise it would diverge. For the first case, the limit of that un, as you can notice, the degree of the polynomial up is bigger than the one down, so that limit would be infinity. And the degree up in the B part is smaller than the one down, so the limit would be 0. In C, the degree of n up is smaller again than the one down, so the limit will be 0. In D, the limit is also 0. And in addition, that is a GP with common ratio half, and the absolute value of R in a GP is less than 1. The GP converges. So at the end, we have A as the sequence that will diverge. In number 9, given a sequence un for n greater than or equal to 1, which one of the following statements is true? If un is bounded, then it converges. This is not always true, because there are divergent sequences that are also bounded. In the second part, un converges, then it is bounded. Yes. The reason is that once un converges, it does so at a particular value, and that value becomes one of the boundaries of the sequence. If un is bounded if and only if it converges. It's not always true. If un has a limit, then it converges. This is not also true, because the limit can be infinity, or it can be some value that is not unique. There are cases where the limit can be plus or minus a certain finite value, like 3. In that case, it's not unique, but the limit is there, and so it has to diverge instead. In number 5, which one of the following sets of vectors is a basis for R squared? We have this, so this. The answer is C. For a set of vectors to be a basis for a particular vector space, one of the conditions is that the vectors should be linearly independent. And if the columns of the vectors form a square matrix, then a quick way is to get the determinant of the square matrix. If they should be linearly independent, then the determinant should be different from 0. It is only C where the column vectors, the matrix formed by them, has a determinant which is different from 0. The others have a determinant of 0. And so that's why the answer is C. Number 10, to find the inverse of a permutation, the shortcut would simply be to look at the way the images are being mapped back to their objects. So I simply mark the images back to their objects and reorder, a quick way of getting the inverse of that permutation. I will start with 1 because it's supposed to be 1 mapped to something, 2 mapped to something, 3 mapped to something, 4 mapped to something. And so I begin from down, mapping upwards instead in the opposite direction to get that inverse. So 1 would map to 3 in that inverse, 2 would map to 4, 3 will map to 2, and 4 will map to 1. For 1 to map to 3, I look at the first entries, I get 1 to 3, 1 to 3. So B and C should be where the answer is found. To confirm, 2 maps to 4. In B, 2 instead maps to 2, so B is out, and 2 maps to 4 in C, so C is the answer. And you can see that 3 maps to 2 here, and 4 maps to 1 to confirm. If you can verify now, you would see that permutation P composed with the inverse would give you the identity permutation. Number 11, which probability distribution model is best suited for modeling the scores in an examination? Binomial, geometric, Poisson, the normal. The normal actually is used in most modeling systems. It has a bell shape and usually the values of the variable cluster around the mean. As you are moving further from the mean, you have very few values occurring in the distribution. And usually marks or the scores in an examination follow that distribution. If this is mu, the mean, you discover that in an exam, most of the scores always cluster around the mean. Most of the candidates score marks around the mean value. And you have very few cases scoring marks away from the mean, scoring very high marks or scoring very low marks. There are very few of them. So this is the variable x, and then this is the frequency. So this system is best for modeling the scores in an examination. So the normal distribution should be the answer. In number 17, given that the line y equals x minus b is an asymptote to the curve this, you have a rational function which is made up of purely polynomials. To get the oblique asymptote, because this is actually an oblique asymptote to that curve, we can use long division or we use the limit method. But long division seems appropriate, so we divide x squared by x squared minus ax by x minus 1. X squared divided by x will give x. Multiplying back, we get x minus x. We get x squared, minus x. And subtracting, we have negative ax plus x, which is the same as negative a plus 1x. And dividing again, we get negative a plus 1. And so this is the quotient of the division, which usually gives you directly your oblique asymptote. So if we compare now the constant terms of the asymptote, we'll see that negative b equals negative a plus 1. And so b would be negative 1 plus a, which gives you D as the answer. You can use the limit method where you have to say negative b is equal to the limit as x tends to infinity of f of x minus the term in x there, which is x. You get that limit, you will still have the result. In number 12, a particle of mass m falls against a resistance per unit mass proportional to its velocity v. In that case, a positive constant. The terminal velocity. The resistance per unit mass is actually r over m. And if it is proportional to the velocity, then it should be equal to some constant k times the velocity. So that the resistance then should be mkv. And for vertically downward motion, the leading force is mg minus the resistance mkv equals ma, according to Newton's second law of motion. The m's would cancel, and then at the moment the particle is moving with terminal velocity, the acceleration is 0 because terminal velocity is a constant velocity. So all this should give 0. So that I can now talk of kv equals g, and so the terminal velocity v should be g over k, which gives c. In number 18, the contrapositive of the statement not p implies cure should be b. The fastest way of getting the contrapositive of an implication is to find the converse followed by the inverse, and this is simply done by switching the positions of the two sides and negating both sides. So when I switch the positions, I get cure implies not p. When I negate both sides, I now get not cure implies p. So it should be something like negation of the converse, which gives you not cure implies p. Sorry, the negation has to be of individual terms. And then you have this. This method would also be used in the case where this was instead given as logically equivalent. So you could have not p implies cure is logically equivalent to, and you still have all these options. You would still use this method. You switch positions and negate both sides to have the answer quickly. Of course, we know that the contrapositive is always logically equivalent to the implication. That is why the method also applies there. In number 19, the velocities of a sphere before and after impact are this and this respectively. Given that the sphere is deflected through a right angle, the value of lambda is this goes 0, 6 goes 3 lambda. The answer is A. So you should know that the angle of deflection is always the angle between the velocities before and after impact. And if this angle is a right angle, it means the angle is 90 degrees. And so those two vectors should be perpendicular to each other. Being perpendicular means their dot product should be 0. And so we get negative 10 into negative 1 plus 4 into negative 1 plus lambda into negative 3 equals 0. And so negative 3 lambda will be equal to negative 6. Lambda will be 2. In number 13, the answer is A. How did I get it quickly? The period generally of motion that is simple harmonic is supposed to be 2 pi over omega. And omega being the angular speed in this general equation for simple harmonic motion this coefficient of x is always omega squared. So we should be talking of 2 pi over the square root of 4, which is 2. And that gives pi. In number 14, if f of x equals 1 minus x squared plus x cubed, then the equation of f of x equals 0 has a solution on the interval. Usually, according to the intermediate value theorem, when there is a root of f of x in the interval a, b, it should be such that f of a times f of b is less than 0. That simply means f of a and f of b should have opposite signs. If I start to investigate each of these intervals, beginning with 0 will be a good option since I can have the image of 0 easily. F of 0 is 1. And if I move to f of 1, I get 1 minus 1 plus 1, which is 1, and it's positive. So f of 0 and f of 1 are positive. That means it's not a sign change. The signs are not opposite. The next consecutive integer should be negative 1. So f of negative 1 should be 1 minus 1, which is 0, plus negative 1, which is negative 1. So there's a sign change for f of 0 and f of negative 1. And so the answer will be B. For number 20, we have B as the answer. Usually when you see an integral in which we have the limit as a real number, negative of a real number to the positive of the real number, then we need to verify the parity of the function involved. And if the function is even, then the integral will simply be twice the integral from 0 to the upper limit. And e to the absolute value of x is actually even. That is why the answer gives B. If you can verify, you will see that e to the absolute of negative x is equal to e to the absolute of x. That simply means that f of negative x gives f of x, and that is the characteristic of an even function. If it were odd, then this integral will be 0. In number 21, the maximum value of this function should be 5, should be C. Actually, to have a maximum out of this function, it should be when the denominator is at its barest minimum. And usually cos f of x generally is greater than or equal to 1. That means the least value of cos 2x in this case then is 1. And so this function will be maximum when cos 2x is minimum. So you get 2 all over 3 into 1 plus 2. So 2 all over 5 is the answer. And this other one, the answer is B. How do you get it quickly? First thing, you notice that when f of x lies between two functions, the limit as f of x tends to whatever value should be gotten easily if we can apply the sandwich theorem. It actually says if these two hold, if this statement is holding, then if the limit of this function to the left and that of this function to the right are the same, then the limit of f of x is also the same. And the limit of the left hand side already, that should be the same as 1 all over e to the x into that. And the limit of all that denominator, this should be 1 all over e to the x into 1 plus x. And the limit of all this denominator is infinity. So 1 over infinity should give you 0. This other one would give you still 0. Substituting infinity directly leads to an indeterminate form. So we use L'Hopital's rule. The differential of ln x is 1 over x, and the differential of x is 1. So 1 over x tends to 0 as x tends to infinity. And so this limit being 0, this other one being 0, the limit of f of x as x tends to infinity is also 0 according to the sandwich or the squeeze theorem. In this other one, this cross this gives this, then the value of lambda, we should be talking of negative 1 being equal to 2 into 1 minus lambda into 1, which gives negative 1 equals 2 minus lambda, so lambda equals 3. Actually, a rapid way of getting this cross product would be to do it this way: 2 lambda 0 for the first vector cross 1, 1, negative 1 for the second, giving negative lambda 2, negative 1. And to rapidly get lambda, I will just equate one component on the left to that on the right. If I take negative 1 on the right, it should correspond to the component on the left when I do the cross product. A rapid way is to cancel the k components. Since I'm comparing the k components on this side, I cancel the k components on the cross product. Then I now get the determinant of the 2 by 2 matrix that results from that cancelling, which is simply obtained by the extreme times the extreme minus the middle times the middle. So it gives you 2 times 1, which is 2, minus lambda times 1, which is lambda. And then to quickly get lambda, I would just equate any one of the components. So I take negative 1, the component of k on the right should be equal to the component of k on the left when I do the cross product. Now to quickly get the component of k on the left, I cancel the components on both sides and then find the determinant of the 2 by 2 matrix that results, which is simply this extreme times the extreme minus the middle times the middle. So 2 times 1 minus lambda times 1. This gives this, and so lambda will give you 3. In number 22, the coordinates of the point P on the unit cube is, we have x, we have y, we have z. So this is C, and it's simply obtained by looking at the way the point has been displaced. Along the x-axis, P has moved by 1 unit, so the x-coordinate is 1. Along the y-axis, P has not moved. It lies on the floor, so the y-coordinate is 0. And along the z-axis, it has moved by 1 unit to find itself here. So the z-coordinate is 1. In number 23, a function f is given by this, and the function f, we're required to verify whether it is continuous at x equals 0, has removable discontinuity, is undefined at x equals 0, has no limit at x equals 0. So actually there are 3 conditions for a function to be continuous at a particular value of x. The first thing is that the limit as x tends to 0 from below of f of x should exist. And that limit is obtained simply by substituting 0 in the upper function there. Substitution leads to an indeterminate form as sine 0 is 0 over 0. So I use L'Hopital's rule there. Sine x differentiated gives cos x, and so cos 0 is 1. All over 1, of course, gives 1. Then the limit as x tends to 0 from below is obtained by substituting 0 in the lower function. Substituting 0, we get 0 squared plus 1, which is 1. The third condition is that f of 0 should exist, and f of 0 is equal to 1. 0 is defined, the function is defined for 0 greater than or equal to, for x greater than or equal to 0. So 0 is in the domain of this part down. So f of 0 exists, which is 1. So you can see that the limit to the left of 0 is 1. The limit to the right of 0 is, so this is plus here. To the right of 0 is 1, and f of 0 exists. So this function is continuous. So the option A is correct. Then for B, for the function to have a removable discontinuity, it should be the case where the left limit is equal to the right limit, but is not equal to f of the continuity value. And so this doesn't hold, because if it were the case, this f of 0 should be different from 1. To say that f is undefined at x equals 0, of course, is not true, because f of 0 exists. And to say that it has no limit at x equals 0, the limit exists, which is 1. So the other options are not correct. In number 28, a compound pendulum oscillates through a small angle theta about its equilibrium position such that this holds. Usually this equation with d theta dt or theta dot squared usually results from the energy equation when you conserve mechanical energy of the oscillating compound pendulum. And to get the period, actually, you have to differentiate this equation. So a quick way of getting the period would be 2 pi the root of this coefficient times 2, which is 20a, divided by the coefficient of cos theta on this side, which is 4g. And this gives us 2 pi the root of 5a on g, which is d. So actually, to go by the solving, we have to differentiate this equation with respect to t. So if I rewrite it as 10 a theta dot squared equals 4g cos theta, when I differentiate with respect to t, I would have 20a theta dot, and I'm using the power rule here. So it's like bringing down 2, subtracting 1, and then differentiating the bracket that has been squared. So theta dot has been squared, so we differentiate theta dot at the end according to the chain rule. That should be equal to 4g cos theta differentiated with respect to t. I don't have t, I have theta. So I differentiate with respect to theta, which gives negative 4g sine theta. I have to multiply by theta dot as the chain rule specifies. Theta dot will then cancel, and I have that theta dot dot equals 4 also cancels to give 5 here. Theta dot dot equals negative g over 5a sine theta. For small angles, sine theta usually just approximates to theta. And you can see that this is equivalent to simple harmonic motion, which usually is negative omega squared x. This one is rotational simple harmonic motion, while this one is linear simple harmonic motion. When this happens, so you compare, you see that this coefficient of theta, the absolute value represents omega squared. And so t is 2 pi over omega. And omega being the square root of that coefficient, there we have the square root of 2 pi, the square root of the inverse of that, which is 5a on g, and that corresponds to d as already given by the shortcut. For number 24, we have that dy dx equals x minus y, and x equals 1, y equals 1.1. Using the approximation, the value of y when x equals 1.1. Actually, this is Euler's formula, and this coefficient of dy dx is always h, the step length. So h equals 0.1. And the fact that x is 1.1 while x naught is 1 implies that it is x1 we are dealing with, because x1 is supposed to be x naught plus h. And so the corresponding y value for this should be y1. To get y1, then I replace every n in Euler's relationship by 0, so I get 0.1 dy dx naught approximately equal to y1 minus y naught. 0.1 into dy dx naught is actually here. Dy dx naught will be x naught minus y naught. X naught minus y naught is 1 minus 1.1, which is negative 0.1, equals y1 minus y naught, which is 1.1. And so y1 should be 1.1 minus 0.01, which should correspond to 1.09, which is A. For number 29, the unit digit of the number this plus this plus this. When we are talking of unit digit, it is about modulo 10, because we're going to be dividing numbers by 10 and writing down the remainder. So unit digit actually has to do with modulo 10. And for me to evaluate this, I will first reduce the bases into numbers in modulo 10. Simple numbers in modulo 10. Also using congruence. 19 in modulo 10 is actually 9, which is also negative 1. So that base could be just negative 1 to the power 1983 plus 11 in modulo 10 is 1. When you divide 11 by 10, you have a remainder of 1 raised to that power. And 9 in modulo 10 is 9, but it is also equivalent. It is also congruent to negative 1. The choice of reducing the numbers 9 into negative 1 on these two cases is for you to evaluate this exponent easily. Negative 1 raised to a power that is negative 1 raised to a power that is odd give back negative 1. So this is negative 1 plus 1 raised to any power is 1, plus again negative 1 raised to an odd power, which is negative 1. So overall we have negative 1 as the answer. And negative 1 is congruent to 9 in modulo 10. So the answer is D. For number 25, let E, F, G be eccentricities of hyperbola, ellipse, and eccentricity of hyperbola, ellipse, parabola, respectively. So which of these is correct? Actually, to get the relationship on which is greater and which is smaller of the eccentricities in a conic sections, we use this mnemonic SESH, or rather SEF. Circle is less than ellipse, which is less than parabola, which is in turn less than hyperbola. So that is the order in which the eccentricities are related. So the one for a circle is 0. The one for an ellipse lies between 0 and 1. And the one for a parabola is 1. and then the one for hyperbola is greater than 1. So we have that. And so the one that is 0 would be less than the one that is between 0 and 1, which is less than the one that is equal to 1, which is less than the one that is greater than 1. And so in that relationship, the one for the hyperbola, which is E, should be the highest. And so it is D that satisfies that relationship. In number 30, we have again the cross product of two vectors giving another, and we are asked to find an unknown. I have the I component here being 0. And again, if I use the K components, I strike it, and the coefficient is -1. It should give me striking the K components of this other side and finding the cross product of what is left, which means the determinant of the 2 by 2 matrix. I get A times the extreme there, which is -A, and 2 times 0, which is -0. And so A equals 1 in this case. For number 26, which one of the following functions is bounded in R? This is simply testing your knowledge of all these standard curves, the standard curves of these functions, which you are supposed to know. Cos x is not bounded. We just have that cos x is greater than or equal to 1. Sin x is not bounded, and e to the negative x is not bounded. It is simply greater than 0, but tan x lies between -1 and 1. And so it is the one that is bounded. For number 31, two particles A and B move on curves RA equals that, RB equals that, respectively, for some parameter t, the shortest distance between the particles. Usually, to get the shortest distance between two particles in a situation like this, we get first the magnitude of the displacement vector of the two position vectors, and then minimize it usually by differentiating and equating to 0, solving for t, and then substituting back to get the shortest distance. The process being long, if it appears in paper 1, you should suspect the fact that the two lines or the trajectories of the two particles should intersect. And this is actually the case. For them to intersect, RA should be equal to RB for some value of t. So 2 equals 2t gives t equals 1. 5t equals 5 gives t equals 1. So there is a unique value of t for which RA equals RB. And so the two particles, their lines of trajectory intersect. And once they intersect, the distance between them normally should be 0. Or the shortest distance between them should be 0. And so A is the answer. The normal approximation to the Poisson distribution X with mean lambda. When mean is lambda, with mean 1/4. When the mean is 1/4, we talk of lambda equals 1/4. And a normal distribution should follow this parameter, should be the mean and then the variance. And if we approximate then a Poisson distribution by the normal distribution, we should be talking of X following the mean, which is 1/4. And for a Poisson distribution, the mean and the variance are the same. So the variance will still be 1/4. So this corresponds to B. For number 32, the limit as x tends to 1. Direct substitution gives 1 minus 1, 0, 2 minus 2, 0. L'Hopital's rule can then be used. So we differentiate up, it gives 2x. Differentiating down, differential of 2 is 0. The differential of this should be negative half into x squared plus 3 to the power negative half dot 2x, the differential of the bracket, using the power rule here. This will cancel this, and then inverting the rest, you get negative 2 the root of x squared plus 3. So the limit of this one now will simply be negative 2 into the limit tending to 1 as x tends to 1. So I substitute 1 squared plus 3. The square root of that, square root of 4 is 2. Negative 2 times 2 is negative 4. And the argument here at z should be the argument of 1 plus cos 2 theta plus I sine 2 theta. First convert this to polar form, and the argument now will be tan inverse of theta, tan inverse of the imaginary over the real, which is sine 2 theta over 1 plus cos 2 theta. This actually is identical to tan theta, which is tan inverse of tan theta, which then gives theta. So the answer is C. You can prove this. It's actually a very common identity in trigonometry. It always gives tan theta. For number 34, the general solution of the differential equation, this is answer is A. So this is actually the equation of simple harmonic motion, which has the auxiliary equation being having complex roots, and it always gives something of this nature. It's either you write it as A cos omega t plus lambda or A sine omega t plus lambda. That is usually the general solution for this type of equation. So knowing that is very useful in answering the multiple choice. In this 39, we have an improper fraction to express in partial fractions. So first start by dividing, and the degrees being the same up and down, the highest degrees being the same. 2x squared divided by x squared will give 2. So the partial fraction should be 2 plus something, and so B or D should be the option. Now we discover that x squared minus 4 is still factorizable. It's difference of 2 squares. So we should be talking of the remaining part being this, and B then corresponds to the answer. If x is 0, we should be talking of x naught being y1 minus y naught, and dy dx naught is 1. So we should be talking of h into 1, approximately y1 minus 2, and so y1 should be h plus 2, which corresponds to B. In number 40, we have a particle moving in a straight line OX and has a displacement x from O at time t, where x satisfies this equation. For this equation to be damped harmonic, we have to first compare with the standard equation, which is d squared x over dt squared plus 2k dx dt plus n squared x equals 0. And so the damping term being this one, we need the value of k. 2k equals 2, k should be 1. The damping factor is always given by e to the negative kt, which is e to the k being 1, so negative t, which is then a. Which one of the following real functions is continuous on R? Ln x is not continuous on R. It is restricted for x greater than 0. x over x squared plus 1. The denominator is not restricted. It takes all real values of x. So the function 2 takes all real values of x, and so should be continuous on R, while this other one is restricted for x greater than -1. This other one is not defined for theta equals pi on 2 and multiples of it. This other one, if we simplify the equation, we get 6 cos x equals 3. And so cos x equals half, but generally cos x is greater than or equal to 1. So this value, cos x, is never less than 1. So this has no solution because the intersection of cos x and half does not exist. There is no intersection between cos x and half. So this equation has no solution. And so this one too should not have. 41, the remainder when -84 is divided by 9, should be D. Simply get a multiple of 9 that is more than 81 and then subtract 81 from it. So -84 plus 90, actually we're using the congruence properties. So we should be talking of -81 should be congruent to a certain value in modulo 9. For number 42, the work done when the point of application of a force is given a displacement d is usually force and displacement are linked. The work done by a force when it does a displacement is linked with the dot product. So D is the answer. For number 43, given that f of x equals the integral from 0 to x squared of f of t dt, f prime of x should be this should be D. Actually, from the first fundamental principle of calculus, when you have integral from a to x of f of t dt, f prime of x would simply be small f of x. But if this upper limit is not x, then I have to use the chain rule, whereby I first get the differential of the function by substituting x squared in the function. So it gives f of x squared, and then differentiating again x squared to have 2x according to the chain rule. So the answer is here. For number 44, a tangent at the pole of the polar curve, this should give a r equals 0 when there is tangent at the pole. So 2 should be equal to 4 sine theta. Sine theta should be half. Sine inverse of half being 30 gives a as the answer. A particle P moves on the curve r equals this. The distance of P from the origin when t equals 1. The distance is supposed to be the magnitude of r at t equals 1. When t is 1, I have 3i plus 4j, and the magnitude of that is 5. The physical quantity y is such that y of t equal to e to the -1 over 20t. This quantity can be modeled by the differential equation. So first I have to write y equal to e to the -1 over 20t. If I differentiate with respect to t, I get dy dt equals -1 over 20 dot 2e to the -1 over 20t. And this actually gives us y. So this is -1 over 20y. And that corresponds to B. For number 46, given that f of x is this, where f is defined on the interval -4 to 4 as shown, On what interval is f increasing? So this is the graph of f prime of x. And for f of x to be increasing, f prime of x should be positive. You can see that f prime of x, which is defined by this small f, is positive between -4 and 0, and then negative between 0 and 4. So it will be positive between -4 and 0 implies that f of x is increasing in that region. So -4 to 0 is the interval. The vector, I move here. The moment of inertia of a uniform disk of mass m and radius a about an axis through its center and perpendicular to the plane of the disk is this. The moment of inertia of the disk about a tangent in the plane of the disk. Actually, the tangent is here and the diameter is parallel to that tangent. I diameter is supposed to be 1/4 ma squared. If you apply the perpendicular axis theorem, this will be the diameter 2 and the one perpendicular to the disk and through the center, which is given here by the perpendicular axis theorem, gives this, which you should master because it's very common in questions and it's not in the formula booklet. And so I'll use now, since this one is passing through the center, I can use the perpendicular, I can use the parallel axis theorem to get the one now at the tangent, which should simply be plus the mass of the disk times the square of the distance between the parallel axis, which is a, the radius of the disk. So ma squared. This times this gives 4 ma squared plus ma squared, 5/4, which is this. Here, given that a star b equals a plus b minus 1, where star is a binary operation on R, if the identity element is 1, then the inverse of x is, usually the relationship is that x inverse star x should give you the identity being 1, and this occurs for all x real numbers. So the binary operation says x inverse plus x minus 1 should be equal to 1. So x inverse should be then 2 minus x, which is b. A vector component of the force this in the direction of this. Usually it is given by f dot the unit vector in the direction of that vector. This gives the component of the force, but if we want the vector component, I have to multiply again by the unit vector. And so I'll be talking of the unit vector of this being that vector over the magnitude 1/5 into -4 j plus 3k. I have to dot it with f. When I dot it with f, I should have 3i minus j plus 2k. And that dot product should be 1/5 into 0 times 3i, which is 0, -4 times -1, which is 4, 3 times 2, which is plus 6. And that should give 2. And then 2 times now the unit vector of v, which is 1/5 into -4j plus 3k. And so the answer should be 2/5 into -4j plus 3k. And option A should have been the answer, but it's not. And the others do not give, and the others don't give too. So the option is not in the answers, if everything being equal.